Welcome to Lecture 5. In this lecture, we're going to wrap up Unit 1 and move on to Unit 2. So to summarize what we've discussed so far in Unit 1, we started off with the toolbox where we discussed units and vectors, and I mentioned that if you are not quite proficient at using vectors, adding them, resolving them into components, and so on, that you should take the time to carefully review Chapter 1 in your textbook. After opening up that toolbox, we went on to start defining quantities that are going to be necessary to start discussing motion in 1 and 2 dimensions, and those quantities were displacement and distance. We talked about the difference between those two, speed and velocity, and also acceleration. Then we went on to discuss motion in 1 and 2 dimensions using our kinematics equations of motion, and also the special case of free fall as it applies either to 1 dimension where an object is just being dropped or thrown up or down vertically, and also 2 dimensions where we add in there an x component to the motion which isn't accelerated because the only acceleration present is that due to gravity, and in that case you have what we would call projectile motion. So to recap the things we discussed with the quantities related to motion, displacement we decided was going to be the difference between the initial and final position of an object, which does not necessarily depend on the path. It just depends on where you were compared to where you are now. And then we talked about velocity and acceleration, velocity being the time rate of change of your position and acceleration being the rate of change of your velocity. And so with acceleration, that means that you could be speeding up or slowing down or changing directions. With our kinematics equations of motion, we have in there explored 2 of these 3 types of acceleration. Speeding up, we did an example with a car, speeding up and slamming on the brakes, and slowing down. And also with the free fall, there's a speeding up that occurs there due to gravity. One thing we haven't yet explored is the possibility of acceleration due to changing directions, so I want to briefly go over that before we conclude Unit 1. So a good example of acceleration due to changing directions is, for example, an orbit of a planet around a star, say the Earth around the Sun. We're going to approximate this orbit to be circular for the purposes of this discussion. In reality, it isn't quite circular. The Earth and all the planets travel on elliptical paths around the Sun, but it's approximately circular, and the Earth is traveling approximately at the same speed as it goes around the Sun. So when you execute this kind of an orbit, you are constantly changing directions. If I were to draw the velocity vector in the point depicted here, it would point tangential to this circular orbit's trajectory, and then later in the Earth's orbit, say a quarter of a year later when it's over here, then I would have a velocity vector pointing in this direction. So the magnitudes of these 2 vectors are meant to be the same, but the direction is changing. And so the question here is, what direction must the acceleration vector be pointing in order to achieve this change of direction of the velocity vector? And we can go through and deduce what this has to be. If the acceleration vector were pointing in the direction of A, what would that do? Well, that would increase this velocity vector in this direction and make it faster and faster tangential to the orbit. So that's not what's happening. The Earth isn't flying off in a tangent at an ever-increasing speed. Likewise, C pointing opposite of A would slow this vector down, and it would just make the speed lower, but also in the tangential direction. If the acceleration were pointing in the direction of B, then that would cause the velocity to veer off in this direction, right? Change directions that way, and that's not what's happening. So what we can conclude is that it has to be D, the direction of the acceleration, pointing in towards the center of the Sun. And so because this kind of change of direction in a circular motion points in towards the center of the circle, we call this centripetal acceleration. And centripetal acceleration is going to be quantified by v squared over r. So what this is meaning is that the faster we are going, the more centripetal acceleration there is in our circular motion, or the tighter the turning radius, in other words, decreasing this r value, would result in a higher acceleration, centripetal acceleration rate. And this you can check with your own experience. If you're going around a bend in the car at a high rate of speed, you can feel that centripetal acceleration on your body, and the tighter the turn, the more you're going to feel that. But this equation, along with some basic information about the Earth's orbit, getting back to the example we were just discussing, is enough for us to quantify what the centripetal acceleration is on the Earth as it travels around the Sun. So this is the radius of the Sun's orbit in meters. So that's the average distance between the Earth and the Sun, which in miles that we may be more comfortable with is about 93 million miles. Okay, so this piece of information plus a couple geometric arguments in the equation I just showed you is sufficient to figure out what the acceleration rate is of the Earth around the Sun. So the geometrical argument that we need is that as the Earth travels around the Sun, if we're approximating it as a circle, it traces out a circle of circumference 2 pi r, where this is my r value. So this is the distance the Earth would travel in 1 year. And I know that when the Earth completes a full orbit, that is equal to 1 year, which I can then convert into seconds. So this is a distance and this is a time. If I take distance divided by time, I can tell you what the Earth's average velocity is around the Sun. And it turns out to be a fairly large number, almost 30,000 meters per second. So you might expect that's going to give us a high rate of acceleration based on the equation being v squared over r, but remember that this is a huge r, 10 to the 11 meters. And so when you actually calculate it, you find that the centripetal acceleration of the Earth around the Sun is 0.006 roughly meters per second squared. So that is actually much smaller than, for example, g near the surface of the Earth, which is 9.8 meters per second squared. But that is because of the great distance between the Earth and the Sun. And when we start to study gravity, we'll begin to understand that gravity drops off very rapidly as a function of the distance, and so that's a sensible reason that we have such a low acceleration rate, even though the velocity is relatively high. Okay, so with that example, we've explored all of the types of acceleration that you could have, speeding up, slowing down, and changing directions. And so I want to then get back to these kinematics equations of motion that we were discussing before and just reiterate that we can do this in either 1 or 2 dimensions. And when we do it in 2 dimensions, we need to be careful to resolve the velocity into its components. And if we don't know anything about time, it's possible that we could use one of these time-independent equations to help us. We saw some examples of that when we looked at the car on the track, the couple examples we did there. And for the special case of free fall, we're acknowledging that the only acceleration present is that due to gravity. So there is no acceleration in the x direction whatsoever. And in the y direction, the only acceleration is due to gravity. So we may as well just plug in minus g into these equations of motion instead of specifying it as plus a in the y direction. Okay, and then finally when we discussed baseball, we talked about the possibility of using the range equation. This is derived from some of the other equations of motion, so it's nothing magical going on here. But the important condition in order to use this equation is that the object return to its initial y position. There cannot be a height change, otherwise this range equation is not valid. It's based upon that assumption. And then we said that if you can't make that assumption, you can always use this other derived equation, which is the equation of the path, which is a time-independent equation. It's rather complicated, but it can be used. For example, in one step, we saw how this solved for the distance that was traveled of a baseball. Okay, and so that basically wraps up Unit 1, and the things that we've discussed in Unit 1, that is describing the motion, have not actually explored the question of what causes the motion. So for that we need Unit 2, where we study dynamics, which is the cause behind the motion that we're seeing. In order to study dynamics, we're going to need a couple concepts. One is the concept of a force. Okay, we're going to talk a lot about forces in Unit 2. We can loosely think of a force as any kind of interaction between two objects, such as a push or a pull, that's going to change the object's motion. Force is a vector quantity, meaning that it has both magnitude and direction, and so that means that when we start adding these things together, we add up and consider the net force on an object, we have to take a vector sum of all of those forces. We need to make sure that we are adding the components properly the way you would for vector addition, and we'll do a quick example of that before we start getting into Newton's laws. But one thing I want to mention here is that the SI unit of force being the Newton, remember in the first lecture that I said that other units that we're going to encounter in SI are basically derived units that can be thought of as a combination of those fundamental units, kilogram, meter, and second. And so a Newton is actually equal to a kilogram times a meter per second squared. And so this gives you a hint right away at what kind of quantities might be involved that are going to equal a force. One of them is the mass, how much stuff is in an object, and this is going to affect the way the object accelerates under the influence of a net force. And the other is meters per second squared. Well, that's an acceleration rate. So you can see probably an equation you've already heard of, force equals mass times acceleration, is basically built into this unit consideration right here. Okay, so before we start discussing Newton's laws, however, let's think about forces strictly from a vector point of view. Let's suppose that we have two forces acting on this ring here that you see in this example, both of which are the same magnitude and directed as you see here, where these thetas are equal to one another. One is pointing off towards the northeast direction and the other towards the northwest direction. And so the question becomes, if I want to balance the forces on this object so that I have a net force of 0, in other words, I want to cancel these two vectors with a third vector, what does the magnitude of this vector need to be? And I've already given to you that this vector is going to need to point completely down, but you can reason through why that is if you think about the components of the two other forces that are acting on this ring. Well, the x component of this one on the right hand side is going to look like this, and the x component of the one on the left hand side will look like that. And you can see that this fx and this fx should effectively cancel one another. And that's why the only thing I need then to cancel out is really the y components of these two vectors with this question mark third vector. Okay, so let me draw the y components here. So this is the y component of the vector on the right, and this is the y component of the vector on the left, and I've made them the same length because they are the same magnitude of vector and they're pointed in the symmetrical directions. Okay, and so these fy's are exactly going to be equal to one another. So really I just need to figure out what one of them is equal to and then double it, right? And then that will be the effective vector that is pointing up. Okay, well, that's just a matter of resolving my vector into its component, because I know that Fy in general from regular vector properties that we've already discussed is just going to be the magnitude of the entire vector times sine of theta. So that means that the magnitude of the vector in the down direction, if I want to cancel that up in the up direction, then I just basically need double of that, 2 f sine theta, which corresponds to choice D. Okay, so without even going into Newton's laws, you can see how we can think about forces as vectors. We're not doing anything necessarily different in terms of vector components and vector addition. But now we're going to bring in Newton's laws to give us a little more insight as to what happens if vectors like this, if the net force cancels and gives us 0, or if it doesn't cancel and gives us some non-zero value. So Newton's first law tells us that if an object is acted on by no net forces, it's going to move with a constant velocity. Now that constant velocity could include the possibility that the velocity is equal to 0. So sometimes you'll hear Newton's first law being said that an object in motion stays in motion and an object at rest stays at rest. That's a little nebulous. I think it's better to be careful what we mean and say constant velocity. So constant velocity could include a non-zero constant velocity or zero constant velocity. So if there's no net force, then the object will either continue on the velocity that it has, that is greater than 0 or equal to 0. If, on the other hand, we do have a net force acting on an object, then we're going to expect there to be some acceleration, so this velocity will not stay constant. And we can quantify how much acceleration there will be based upon this equation here. We have to look at the net force, and remember that this is a vector sum, and that's going to equal the mass times the acceleration. So that is to say that the more force we apply on an object, the more it will accelerate. But also the more massive it is, the harder it will be to accelerate the object for the same amount of force. So the mass comes into play here as well. Finally, Newton's third law tells us that basically forces come in pairs. If there's a force on object B from object A, then object B will exert an equal and opposite force on object A. And so these are saying that for example, in notation form, F of A onto B is going to equal the negative of F of B onto A. So they're the same magnitude, they just point in different directions. And this has implications, as we'll see, for analyzing the forces involved in different problem scenarios. So before we start looking at some of those problem scenarios, let's start to enumerate some of the types of forces that you might run into. This is by no means an exhaustive list of all the forces that exist, but these are the common ones that you'll see in some introductory Newton's laws problems. So there are the contact forces that we're going to encounter, such as tension, friction, and something called the normal force, as well as any applied forces that someone might push or pull an object with. And then there's the non-contact forces. Mainly we're just looking in Physics 1 into gravity, which provides the weight on the object. When you get to Physics 2, you'll discuss some other long-range forces, non-contact forces such as the electric force, but for now we're going to constrain that discussion primarily to the weight force. So to explore each one of these type of forces, common forces in turn, the first being tension. Tension is basically going to be thought of as any force that's exerted on an object by way of a rope or a cord or a string. And for our purposes, we're going to assume that the force is transmitted undiminished along the length of the string or the cord. The normal force is basically a force that happens when there's contact between the surface of one object and another, and that contact force is always going to be perpendicular to the surface. Typically you're going to see it portrayed as an example like you see here, where you have some box or books sitting on a table and the table's surface is horizontal, so the normal force is pointing perpendicular to that surface up. But of course this surface could point off in any other direction, perhaps at an angle, and then the normal force will continue to point perpendicular to that surface. That's important to keep in mind. Don't fall into the trap of thinking that the normal force is always quote-unquote up. The friction force, so there's a couple different types of friction that we're going to encounter here. It's going to happen if an object is being pushed or pulled along a surface, and that may or may not include the object actually moving in response to the push or pull. If you push very hard, for example, on a heavy object, you may not be able to get it to move, but that doesn't mean that there's no friction present. There's just a different kind of friction that we would call static friction. Whenever the object actually is moving, then we have what we would call kinetic friction, and that's going to be proportional to the normal force. The constant of proportionality involved here is a constant called mu, and mu is the coefficient of friction. Typically, you'll find the value of that coefficient on a table that considers the type of surface that you're dealing with. A smooth surface will have a smaller frictional coefficient than a rougher surface, for example. And the weight force, the non-contact force that we're going to encounter, is quantified by this equation here, where weight equals the mass times little g. It's always going to point down towards the center of the earth. So in this case, it is always down, right? So when we talked about the normal force, we said it isn't always up. It depends upon how the surface is actually oriented. But for the weight force, it doesn't depend on how the surface is oriented. Gravity always points down. Okay, so I've shown you a couple pictures that have these nice force vectors drawn on them. What we're going to need in order to start understanding how to solve some of these Newton's laws problems is a tool which we call a free body diagram that accounts for all of the forces acting on an object. What we generally do is we represent the object as simply a dot or a circle, and then we draw the force vectors off of that dot, where we account for all the forces that are acting on the object and indicate each one of those with a vector. What we do not include are any forces that the object exerts on other objects. It's only forces that are acting on that object. Okay, so let's take a look at an example. Let's say that we have a book sitting on a table. And we want to start drawing a free body diagram of this book, and we want to know which forces should appear on our free body diagram. If it's just sitting there and we're not trying to push or pull it, we don't need to worry about this friction force. However, we do need to worry about the weight and the normal force. So that corresponds to choice D here of the options listed. So let's go ahead and draw that free body diagram. We have a dot here, as I mentioned before, representing the book so that we don't have to be an artist and draw an actual book. And then we have the vectors, each one for an individual force. And if you're feeling comfortable and proficient at drawing these free body diagrams, perhaps you've done this in previous physics experiences and you feel like you know what you're doing with it, this might not be necessary, but I would recommend having some sort of system, at least as you're becoming comfortable drawing free body diagrams, that helps you make sure that you're including the forces that you should and not including forces that you shouldn't. So one way to do that is to use notation where the subscript indicates explicitly what forces you're talking about. In this example, I have N representing the normal force, and then the first subscript indicates the object that is exerting the force, and the second subscript indicates the object that the force is being exerted on. So N sub TB means the normal force of the table on the book. And WEB indicates the weight force of the earth on the book. And in that way I can see that both of these forces end in B. Remember that my free body diagram should only include forces that are being exerted on the object, and so the second subscript is what corresponds to what object is having the force exerted on it. And I can see that both of these have B for book, so I haven't erroneously included some force that the book is exerting on some other object. Okay, so let's make the situation a little bit more complicated. Let's say instead of one book sitting on a table, I've got two, and I want to look at the free body diagrams for each of these books. So when you're thinking about the top book, the upper book, you may think, well, it's really no different than what I had before of one book on the table. It's just that instead of sitting directly on the table, it's sitting on a book beneath it. And of course that is true, so nothing is going to fundamentally change with my free body diagram for that top book. I will see really just two forces on my free body diagram, the weight force and the normal force that we discussed before. And you might think, well, something else is happening with that lower book because it's got a book on top of it. So it's no longer exactly the same as when it didn't have a book on top of it. Somehow there's a third force involved here due to that top book or that upper book somehow exerting a force on the lower book. And indeed that's true. We're going to need three forces in our free body diagram for the lower book. But we're going to need to be very careful about what that third force is. There's a common misconception or trap that people tend to fall into with this situation, and so we'll see if we can avoid that. So let's talk about it. What of the following forces should not appear on a free body diagram for the lower book? Well, we said using this subscript system that anything that doesn't end in L for lower book should not be included in my free body diagram because I only want to include forces that are acting on the object, not forces that are either acting on some other object or being exerted by the object in question. Okay, so I can see that this is a U and this is a U. This is the force of gravity of the Earth on the upper book. So we don't want to include this, nor do we want to include this, the normal force of the lower book on the upper book, because this lower book is the one exerting the force in that case. But a lot of students have trouble discarding choice C here because they're thinking, well, the top book is clearly doing something and exerting some sort of force onto the lower book. Isn't it the weight of the upper book that the lower book is feeling? Technically, it's going to be equal to that weight, but that's not the force that we're going to actually include in our free body diagram. So what we actually want to include is this contact force. Remember that I said that the normal force can act in many different directions, not necessarily up. This top book is in contact, its surface of this book is in contact with the surface of that book, and that's the force that we're going to include because the normal force of this upper book is exerting a force onto the lower book. And that's what you see here, normal force of the upper book on the lower book. That is the third force to include for our lower book. But I'm going to warn you here that these free body diagrams, this first draft of the free body diagrams, are not quite right. The lengths of the vectors in particular need to be examined here. And so I want to look first at Newton's third law to help me out here. According to Newton's third law, I want to figure out what should have in the first free body diagram the same magnitude as the normal force of the lower book on the upper book. Okay, so Newton's third law, to review, tells us that the force of A on B, the magnitude of that, is going to equal the magnitude of the force of B onto A. So if I do not include the vector symbol here, I've just told you that the magnitudes are equal here. So I don't need that minus sign to talk about the direction. I'm really just looking at the magnitudes here. What that means is that if I'm looking for what equals this force in this free body diagram for the upper book, based on Newton's third law, then I need to talk about some force from the lower book, right? Because it's A and B. By Newton's third law force pairs cannot act on the same object. We have A and B and A here. In other words, the normal force of the lower book onto the upper book has to, by Newton's third law, equal the normal force of the upper book on the lower book. Do you see how those are analogous? Okay, now it's true that this vector, this normal force vector equals this weight vector. That is true for the upper book, but that's not true because of Newton's third law. That's true because of Newton's second law or Newton's first law, where you're thinking about the sum forces on this upper book itself. Okay, but based on Newton's third law, we're able to check this off, that these two should be equal. Now they don't look equal right now, so we're going to need to make an adjustment to our free body diagram. But before we do that, let's just recap what I said a moment ago, that these two and these two are equal, but that's because of Newton's second law, right? So these two are the same. So with all of those things in mind, let's redraw the free body diagrams appropriately with approximately the right length for our vectors. Now, of course, if I were to grade a question in which you were asked to draw a free body diagram, I'm not going to probably break out a ruler and make sure that all of your magnitudes are exactly the way they should be. But you want to try and get it roughly the same so that you can get a good picture of what's actually happening. So when I redraw my free body diagram, I can see now that this vector, I had to increase its length so that it would be the same as this vector by Newton's third law. Now notice that when I did that, I also decreased the length of this vector. Why did I do that? Well, by Newton's second law, where I'm thinking about the sum total forces on this object, which happen to equal 0, I need it to be the case that the normal force of the table on the lower book equals the total of these two in this direction. Otherwise, I would have some net force, just the same way we did with the very first example where we were looking at the ring and how we could balance the forces there. I want the ups to equal the total in the down direction. Okay, and so if I've increased this vector, now if I want it to balance with this one, I better decrease this one. Otherwise, I'm going to have too much pointing down. Okay, so that's why I made this one shorter. Okay, next time we will start using free body diagrams to actually go forward and apply Newton's laws to a problem-solving situation or several of them, and I will talk more about that then.